Well, hello everyone. Welcome to part 9 of my coding tutorial. And if you remember, we were coding DLL injection into all processes. And we're still working in our Windows driver. And today I will try to get to the actual DLL injection. And for that we will be using Kernel APCs, or Asynchronous Procedure Calls. So that's what we will try to do today. Now, it's a somewhat longer subject, and that will conclude our injection, so it might take me a couple videos to actually finish it up. Well, before we go on, there is one little nuance that we need to finish up with our project. If you remember, it was called InjectDLL, so let's open it up. And if we go back to our DLL, and that we were calling FAKE.DLL here, for the lack of a better name, what would be nice to do is to add a resource to it, which is a version. And the reason we would add version to our resource is so that we can actually tell, what the file does for people that want to quickly check. So if we do this, again, it's FAKE.DLL and version. So what I usually do, I put the company name. Well, you can put the name of the developer. In my case, I'll put the name of my website. And file description. I would give it some very short descriptive name. Let's see, I would say test DLL to inject in all processes. Okay, so the version will be the same. The name is FAKE.DLL. The copyright is just what it is. And let's just do, let's say, product name. I would just use the same thing here. So what we do with this version thing is that we basically, again, introduce what this DLL is, because obviously it will be injected into all processes on the system, and so whoever pulls it up, they need to see what this is. They need to know the author, so if there's a problem they can always contact me, and I can explain what that thing does. So anyway, wanted to add this little thing, which is just a little courtesy. Okay, so let's go back to our driver, into our CSection class. And if you remember, we kind of, well, didn't finish, but we concluded one stage where we created a known DLL as a section, and we got its handle. I mean, not the handle, we got the pointer to its object, and we were ready to inject it. Now, let's talk about the injection itself. Now, because we are, when we call this API, let's just trace it back. So it's called from here, and obviously we are calling it as a system from the system thread context here, so have to remember that. Then it's called from getSection, and getSection is a singleton. But let's see, so it's going to be called once, but let's see where this function is actually coming from. This fine window keeps moving on me. Okay, so that it doesn't come from here, but it comes from here. So we actually call it twice, as you can see, for each type of section. And this comes from the moment when we have our DLL, kernel DLL injected to get the pointer to our DLL stats, which will contain a section. And the whole thing comes from the image on load, which is a callback that we set up from this API. Now, if we look up, let's see, where is my web browser? If we look up this API, it will tell us that the callback, let's go to the callback, it tells us somewhere in here that it is executing from within a critical section or some kind of a lock. So in other words, we have to be very careful what we are doing unless we want to really hold off the system. basically we have to perform our creation of our section, and not just creation but also injection of our section, which won't be done here, but it will be done, let's see, it will be done in our onLoad method, right? So when we get our pointer to our DLL stats, which will again contain our section, further down we will have to inject it. So how would we inject it? Well, we can't really do it here because again first of all we're coming from within this critical section, within this lock, but we have to do it later. And one way to do it is to use what is known as APC. APC stands for Asynchronous Procedure Call. So I'm not going to go into details of that, but if you go to my website, which is DenisBabkin.com, if you go to my blog and if you search for Kernel APC, it will have this depth of Windows APCs, aspects of internals of asynchronous procedure calls from the kernel mode. So if you look this blog post up, my friend and we described like certain very technical aspects of APCs, but if you go into general APC internals, there is a link to this blog post, which I copied from this very nice book by this person, that will explain all the specifics. It's a very long blog post. I mean, it's a very long write-up, so make sure to read it. This will basically explain what kernel APCs are. And just to explain real quick, so when you queue an APC, it's kind of like a property of a thread that tells it, hey, we need to execute something. We don't need to do it right now. Right now I just want to queue it, or kind of do it really quickly, kind of like set what I want to do, just basically set a callback. And then the thread or the system will allow you to execute this APC as long as APCs are allowed. Because again, sometimes APCs might be blocked or might not be possible. And in that case, you don't care when exactly, you just need to kind of do it as soon as possible. So that's what APC is. And in case of kernel APCs, they're not unfortunately really well documented. So again, make sure to refer to this blog post, so it will explain how it works. But basically, when you queue an APC, you can provide 3 types of routine. And that's kernel only, by the way. User mode APC just provide 1 routine. So in our case, we have a kernel routine, we have a normal routine, and then we also have what is known as a rundown routine. Now what these routines are, they're basically callbacks that the system will invoke or call when APCs are allowed to run. The first one is the kernel routine that will be invoked. As you can see, it will be invoked first, and it runs at the higher IRQL level, at the APC level, so to speak. So it won't be running at the passive URL. Now then, when this APC actually finishes running, the normal routine is invoked. Now normal routine is optional. In our case, we will be using it. But this routine is actually called at passive URL, or IRQL, I don't know how you call it. And that's where we will be doing most of our work. Now, rundown routine is a special type of routine which is invoked only when our thread is closed before it had any chance to run. Now, this one is just basically something that would allow us to clean up and do all the kind of like, last-minute cleanup if our normal routine doesn't get called. So this is kind of like the concept. Oh, and by the way, when you queue these from the kernel mode, you can specify two modes of the APC. One is the kernel mode APC, which will run at an interrupt. So basically, it can happen at any moment as soon as APCs are allowed. And then you can do user mode APC, which will run when the CPU will actually enter a user mode. That usually happens from when the system is done with the system call, when it goes back to the user mode, and that's when our APC can be invoked. Now again, I will refer you to this blog post, so make sure you run it. I mean, make sure you read it. This is the URL for my copy. And so yeah, that's that. And again, you can, let's see, with this blog post, you can actually read it. Now this one has some additional details of what you can and can't do with APCs, so make sure to familiarize yourself with that. Okay, so this is the theory, and now we need to get back to our project and actually start coding. Okay, so enough talk, and let's get to actual coding. So as I said, right here we will need to inject our section, and we're in driver main, and obviously we're not going to write it here. So let's write a function following this one, and let's see, I think this is the right place. Let's just add it at the end, I guess. Let's see, yep, create known DLL. So now it will return NT status, if my IntelliSense actually helps me. And let's see, this is CSection class, and let's just call it InjectDLL. Right, so very simple. Now it will accept our DLL stats class as a pointer. Let's just call it DLL stats. If you remember, this is a structure that we saved in our singleton that will have all of our needed parameters. So far we have only 2, but we'll add more. And let's add a declaration for it. Now this will be a public method, because we will have to call it from outside of our class. And also let's put a simple comment, which basically says that inject DLL into the current process. And this parameter here, basically DLL info to inject. Now this parameter has to be provided, so let's put assertion here. And since we are dealing with the status, let's declare it and return it, except not that status, but this status. Okay, so this is the basic scaffolding for our API. And just to do some sanity check, let's make sure that our structure is actually valid. And if it's not, well, we can say that this is invalid data. Let's throw assertion and return. Let's see, well, status, let's see what IntelliSense gives us. Invalid parameter. Well, it's such a default generic thing. Let's do invalid parameter mix. Something to just differentiate from other error codes that might be returned. And again, is valid here is just a little structure that will validate that this little structure, is a function that will validate if this structure is filled in correctly. Right now it just checks that we have a section pointer. Okay, so that's cool. So at this point we need to allocate an internal structure, which is called KAPC. I'm sorry, not P, but pointer to this KAPC. This is an opaque kernel mode structure that is used for kernel APCs. Now, and the way we allocate it is we are using well, not heap, but we're using we don't use stack, we use kernel memory for that. And let's call an API allocate pool, And let's be good citizens and actually provide tag. So we need pool type. Now this is important here, and it has to be non-paged-pool. I'll explain this in a minute. Then we need the size of not KPAC but KAPC structure, and then we need to provide our tag, and the tag just has to be something something unique like APC1. That should do. And we have to cast it into our pointer here. So why do we need non-paged pool, even though we will be injecting it from, let's say, you know, URL that does not require it? The reason being is actually explained in one of the blog posts, so I'm not going to go too deep into it. So if you go into my website, let me just copy this URL, and I'm going to paste it here. So basically what happens is that when we queue an APC, and the thread might actually have more APCs queued to it. And if it just happens to be that the thread at that time is running at a higher URL, like for instance a dispatch level, when that APC is queued, not even in your code but somewhere else, the API, the function, will walk back by a double-linked list of APC structures. Well, when that happens, you basically get access to a paged pool if your APC is actually allocated in a paged pool at a dispatch level, which basically is a guaranteed way to get a blue screen of death. So that's the reason why you wouldn't allocate your memory for your APC from a paged pool. Instead, you always do a non-paged pool. So I'm not going to type all of that, but let's provide very quick description why we need to allocate it from a non-paged pool. And let's just say we need, let's see, not we need, but we need to allocate our KAPC from non-paged for details, check, and we'll provide this blog post so someone can just click and read the explanation. Okay, so that's the reason why we chose non-paged pool. Obviously we need to check if, you know, there was an error, failed to allocate memory, and return status memory, let's see, memory not allocated, so that should be enough. Okay, so at this point we are ready to queue our APC, and let's just put a little bit of a comment here for the next developer that might be reading this. Let's just say that because we are called from under a critical section during the onload image callback, initialize an APC to do all the work for us later. Okay, so just a small description. And okay, so we need to set up regular kernel APC. Now I'm saying regular because there's also special type APC. In this case we don't need special type APC. Again, to understand the difference, make sure to read this right up. Now in our case we don't need special type APC, we just need regular. I'll just put it in quotes so that it doesn't raise any questions. And the reason we do the regular is because we specified normal, routine, and kernel mode. Now the reason, I mean, the way you specify special routine is when you don't set the normal mode and normal routine and run your APC in kernel mode. So that's kind of like a quick explanation. Okay, well, let's see. And the API is called KeInitialize. Well, it's not defined. So I have to go back into my, let's see, where is it in driver types? Yep, and actually copy and paste it, because unfortunately it is undocumented. So let me go get the declaration for you. So let me copy and paste it real quick. I don't want you to like watch me type all this stuff. And it has some undocumented parameters here, so let me add them as well. Again, I'm going to do copy and paste because I don't want you guys watch me type all this stuff. So basically, APC environment is just an enumeration of types of environments the API provides. Now, normal routine is just a callback, if you remember. Normal routine, kernel routine, normal routine, and rundown routine, all three of them. So that's what this is. So here's normal routine, the way it's defined. Here's the kernel routine, again, the way it's defined, and the rundown routine, very simple. So that's how we get here. I'm not sure why it's still showing this. Oh, okay, well, obviously it's not found because it's not declared yet. Okay, so now we can actually fill in the call here. So let's bring up the IntelliSense. Okay, the first parameter is our pointer to the KAPC structure that we allocated over here up above. Now the second parameter is the thread that we are running in, and what we are running in is the actual current thread. So that's very simple. Okay, now, oops, sorry. Oh boy, come on, IntelliSense. Okay, now the KAPC environment, I would just specify original APC environment, so nothing fancy here. And then we come to the actual routines. So we have a kernel routine, we have a rundown routine, and we have a normal routine. Now, we have not yet declared these routines, so we'll kind of like leave them as is. Now, the mode, which is important, is a kernel mode. Let's just put a comment here and say that this is a kernel APC. And as a parameter, last one is a normal context, and the normal context is passed into, if you look here, it's passed into the normal routine. So let's pass our parameter, and let's just put a comment here. Pass KAPC as context into our normal routine. Okay, so at this point, that's all we need. Now this function doesn't really do much. It simply just fills in all of these parameters into the internal APC structure. So it doesn't even return any error messages. But what we need to do before we queue our APC, we need to prevent our driver from unloading by incrementing its reference count. So if you remember, as I told you, APC is executed asynchronously. So in other words, we can't assume that it will be run right away. So in the meantime, when APC is queued, technically someone can unload our driver, or they can call driver unload. So in this case, we need to be sure that when our APC is queued in our driver, it is not unloaded. And for that, we will be using our driver object right here that we saved in a global variable, if you remember, right over here. So To increment its reference count, we just use this macro to a reference object, and we provide it right so. Okay? And I'm not sure why. Oh, okay. Well, what we need to do, this parameter is actually declared outside. It's a global variable, so we need to define it as such. And for that, let's go all the way to the top. And let's just say extern C. We'll create a little section here. And we are going to say extern. Oops, no, don't need that. And too many externs. And declare our object as external. Okay. So now, let's see. What am I doing wrong here? Oh, okay, didn't type it right. Okay, so this way it will increment reference count on our driver. So when it is attempted to be unloaded over here, it won't until our reference goes back to 0. Well, so this is our way of preventing our driver, or preventing basically blue screen of death when we deal with APCs. Now this stuff is very important, so make sure to remember that. And since we did this, that we incremented the reference count, we also need to dereference it when APC comes, or if we have an error at queuing our APC. This is also important. So make sure to do that. And besides, we need to also keep our section object loaded for the same reason. And let's say object, a reference object. And what we need is actually go here and provide our section object. Now again, the reason we would do that is because, you know, APC may come later after we try to delete our section, or remove our section, or close our section, or free, whatever we called it. And in that case, we need to make sure that it's not deleted before the APC is actually processed. Okay, well, so we did these precautions, so make sure again that you keep this in mind. This is very easy to neglect because, you know, technically it would work normally, and only in some exceptional situation during some timing issue these situations may come up. Okay, so at this point we can initialize the APC and get it ready for running. And the API is KeInsert, if I spell it correctly, InsertQueueApc. And again, they provide only DPC, but we don't need that. We need APC. And again, it's not declared, so I will have to do the same magic basically and copy and paste it into our undocumented APC section. So let me skip it down here. Now it's very simple. You just provide your pointer to your APC parameter that you just allocated. You provide arguments and priority increment. So let's do it right here. Now the first parameter is, let me just bring it back, is our KAPC, the pointer that we provided. Now then we need to specify system arguments. Now these are akin to a context that will be passed into our callbacks. So here I will just pass our DLL stats. And let's just say that this is system argument 1. Again, just for readability. Points to, and let's provide this structure. Now, next one is not used. Let's just say so. We can technically pass something else if we need to. This is very handy, by the way. And the last parameter is IO no increment. We're not incrementing anything, so that's kind of like good way of basically using default. And the interesting thing about this API is that it actually returns a Boolean, so it doesn't return status. It just says, hey, was it queued or was not queued? And in this case, if it was queued, we need to deal with it. And basically, we can just say queued APC OK, and not return, but do status success. Okay, so we basically say, hey, we are done here. And in this case, we failed. An important thing is that because we failed, we have to do a rollback of this stuff. And remember, we also allocated memory, so we have to roll all of it back. So let's just write it here. Do rollback. Okay, well, the first thing that we need to do is actually log our error. Now let me see if I can get it from somewhere, like how about here? Obviously, logging errors in this case is very important. And we want to say that the API is this. We want to provide our process ID, and we want to provide a section. So pretty much default implementation here. But we need to dereference our objects. This is very important, because otherwise, if there's an error, these objects will not be deleted and the driver won't be unloaded. So make sure to do this. And we call dereference object. I actually need to do it twice. And if you remember, we're doing the driver and we are doing our section. Okay. And the last thing that we need to do, we need to free memory. And we do x free pool. And if you again remember, we have this KAPC parameter, which we did not use. And we null it out to prevent any possible use after free. So again, all this rollback is very important, so make sure that you do that. Okay, well, and that's pretty much what we need to do to queue our APC. That's how we can do our injection. Well, not really an injection. That's what, again, what I'm saying here is that we are queuing it only to have the work done later. So this stuff happens very, very quickly, so we will not be wasting time inside the critical section. And what I also need to do here, just to give some context to the next developer, Visual Studio really likes to help me here by adding additional comments. I'm going to take this and I'm going to put it here, so that the next developer could see what is going on, and so that we can also refer to it from our further further coding. So at this point, we have pretty much everything except of our routines here, or callbacks. Okay guys, before we begin coding our callback routines, there is a little gotcha that I need to explain. Now, if you look into my blog post, the one I gave you, I'm going to copy the link here. There's this little article that my friend and I wrote up, and it's called PS Set Load Image Notify Routine Gotcha. You can kind of refer to it here, but I'll try to kind of quickly show it to you on in example. So I'm going to put this link here, and come on, Visual Studio, stop doing that. So annoying. Let's see, the reason we are coding the way we did, and link here. Okay, so if we take, let's say, our, well, let's just take kernel routine, And if we went here, and let's say if we go back and let's see kernel routine, where is it? Well, let's take normal routine. It's a little bit simpler. If we did, let me just copy the whole thing, I guess. So if we coded our normal routine as such, and then what we obviously need to do, if we did, let's say, where is it, normal routine, right? If we put it here and then ran a code, it doesn't return anything. And then at the end, because remember we referenced these things here, well, we also need to dereference. Well, we can't dereference the driver, but we need to dereference our section. So if at the end, I'm sorry, not the section, the driver, at the end, if we did this, that would seem like a reasonable thing to do, right? So we are done with our normal routine or the kernel routine, and then we need to dereference the object. This is how you can, dereference driver so that it can be unloaded. Again, we need to do this because we actually incremented the reference counting here. So by dereferencing it, we actually say, hey, we're done with it. We don't need it anymore. But look at it, what happens. If you compile this code, the compiler will probably put a call assembly instruction to call this API, right? Well, but then it will actually return, do its work, and then it will call ret to return from the normal routine. Well, by dereferencing the driver, we're kind of saying like, hey, we don't need it anymore, it can be unloaded. So if that happens, when we come back to this return instruction or whatever is here, it might be some pop or to I don't know, to restore something here, to restore the stack frame, doesn't matter. But as soon as we return back, well, this code may not be even present anymore because our driver could have been unloaded. It kind of creates a race condition here because, again, if this API decides to unload it right away, we will get basically blue screen of death because, we returned into some area of code which is not held by our driver anymore. Or everything might work fine until there's some kind of timing condition when this situation happens. So the problem in this case is that we can't really call object dereference object here from within our routine, but we need to dereference it somehow. So in the way my friend came up with, kind of like very nice and ingenious solution, which is described right here, is that he uses a jump instruction to actually call dereference object. So what he does is that instead of a call, he uses jump that will initiate this instruction at the end of our normal routine, with the only difference that the execution will not return back to our driver. Okay, and this is really important to understand so that we do not create a race condition at the end of our routine here. The problem for us is that we are coding in C, and C doesn't provide any way to specify that we want to use jump instruction to invoke our function. Well, sure enough, the compiler, the optimizer, may include it, but it may not. In most cases, it may not, because it has to, at the end, it has to clean up the stack frame and do additional work. So it may actually use a call instruction. Well, in our case, that will be bad, so we can't rely on it. And again, the C specification does not allow us to ensure this. So because of that, guys, we will need to code this in assembly. So what my friend did, and what I also will do here, is that we will create a short stub for the normal routine, for all three of them, by the way, not for the normal routine, that will invoke our C code, which we'll write here in this class. But then when it comes back, it will optionally invoke our dereference object at the end. Now note that it may not invoke it. It may just, sometimes we don't need to do it, because again, obviously we don't have to dereference our driver from all three routines, from all two, from kernel or normal routine. We also need to do it only once, because obviously we referenced it once here. We incremented the reference count. So that's what I will do here in this project. So I hope you understand this. Again, please make sure to check this little write-up here in the blog post. And again, I will provide the link below. Okay, so that's the theory, guys. So again, I'm going to delete this. And we will write all three of these routines as a short stubs in assembly language. And the thing is, I'm going to provide a comment here that these routines are implemented in assembly language, C ASM64 or ASM32.asm. Now we don't have them yet. We need to add them to our project, but this is basically where these routines will be coded in. So let's add those assembly files. Okay, so let's click on source files in our driver, add new item, and as you remember, ASM64 and ASM32. Let's start from 64, call it asm64.asm, make sure to provide ASM extension. And again, because it's assembly language, we need to provide two variants. And let's do the same for asm32, basically for different bitness. Again, make sure to specify ASM extension. In this case, we need to exclude 32-bit ASM file from 64 build, because obviously it's not compatible. And we need to do that. And while we're at it, let's do the same for release, because again, we have 4 configurations, so we need to make sure that all of them are built. Okay, and then if we switch to x86, we need to exclude our 64-bit assembly from release and also from debug. Unfortunately, yeah, there's a lot of monotonous work here with these configurations, but in the long run, that will actually help us. So let's save everything, and we'll get back to assembly into 32-bit assembly later. So at this point, let's code 64-bit assembly stubs. Okay, well, first thing first, we have to provide code segment, and we need AND at the end. And well, let's do, I don't know, the rundown routine, I guess. Let's find our. Now the rundown routine is the easiest, so we do that and proc. And just to make it more readable, let's go here into our driver and just kind of like, I'm sorry, that's not a rundown routine. This is rundown routine. Let's just quickly copy and paste it here. Okay, so rundown routine, I'm just going to put it in one line. And we don't need this instruct, so that we kind of know which parameters it's called with. And let's just say that RCX, because again we're in 64 and that's the calling convention, is a pointer to this structure here. Okay, so at this situation we just need to do what we wanted to do. And what I was thinking is that we would have our callback. let's just, go to a C and actually write the callback so that we can kind of, so I can actually show it to you how it looks like in C and then code it in assembly. Now I will specify it as extern C so that we can actually call it from assembly without using very crazy name mangling. Now, important for us, not for x64 but for x86, is to specify a calling convention. I'm going to use standard call, std call, as pretty much anything else for drivers. And it's not section. Actually, we will not add it to a class. We will just create it as a global function. So again, we can refer it from assembly. And let's say RundownRoutine Procedure. I'm just going to add this little suffix here so that we can differentiate it. And the input parameters are pretty much the same as for our APC. Let's just type it in, I guess. It will be pointer to KAPC that we passed. And let's just make a comment that this is called from the asm64.asm or asm32.asm files for the rundown routine callback. And let's see, the return, this Boolean value here, is important. We need to return true to invoke, and what we are invoking is this thing here. Okay, so if our callback needs to invoke this procedure safely, let's just do invoke safely, this little routine, we need to specify true. And if we don't need to invoke this, we specify false. So that's the whole point of invoking this from assembly. And just to give a little bit more context here, let's just copy all this stuff. And again, so that people know, because again, this, unfortunately, kernel APCs, they're not really well documented. So let's just say that, oops, come on, Visual Studio says that it runs, and let's see if we can just clear this out. Okay, so we put a little comment, and the person can read actually what's going on here. And in this case, in a rundown routine, we actually need to dereference driver. So we will return true, obviously driver object. Okay, so at this point, as you can see, this callback will be called from our little assembly stub. And because we are calling it from our assembly stub, we need to declare it as extern, and this is procedure. And over here, we will call it. And let's make a comment here, though, so that the person knows. First, call our rundown procedure from the C file. Okay, now because we are in x64 and we need to obey the calling convention here, we need to align our stack on 16-byte boundary, and we also need to provide shadow stack. So for that, we need to subtract 4 keywords, and also add one more for alignment. And since we did that, we also need to revert it back here by adding 28H. And again, that's hexadecimal. So we will call our rundown procedure. And the rundown procedure, if you look, it provides the KAPC pointer. In this case, we get it from here, from RCX. Okay, so we don't change RCX and just pass it on directly into it. Okay, and next we need to act depending on return value from from return value. So whatever rundown procedure returns us, again, and return will be Boolean, and that will be RAX in RAX. So we need to check RAX for 0, and if it's 0, we'll just jump, let's say over here, and all we need to do is just return, right? So we don't do anything, we just return from the rundown routine. Now if it is not 0, if it's 1, then we need to invoke this procedure here. Now, as I said, very important, it has to be done with the jump. And if you look at the parameter, it actually needs our driver object. So we need to put it into the first parameter, which is RCX, and we need to use it. But since we are using it, and because it is global, we also need to put an extern statement for it. And this is a Q word. Because again, if you go into our main file where it's declared, it's a pointer, and the pointer in 64-bit assembly is a Q word. Okay, because we have to specify bitness here. Okay, so then we actually need to call this function. Now let's look at it. So let's see, where do we have it? Now if we go to peak definition, you can see that this is not actually a function, it's a macro, and the function itself is object f dereference. So there's like this extra f in here. Now this is a fast call, which means it's the parameter is provided in register, in this case RCX, this parameter here. And so we need to invoke it, so let's take its name and go back to our assembly file and invoke it. Before we leave it like this, there's actually one nuance that we need to look into. Let's go back to my blog. You go to the top, and if you look for intricacies of Microsoft compilers, the case of Curious Imp, if you read this blog post, and basically details the use of this imp. And just to kind of quickly to recap, if you use just the API name from the assembly, it will call a short jump stub itself to redirect to the actual API. It's reading it from the IIT, which is IAT, I'm sorry. It's import address table from the PE file. It's kind of like the way compiler does things, but to prevent this second jump stub, we need to add imp at the beginning here, and that will be direct call to this API. And since we did that, we also need to reference it here. And this is an external reference to the IAT, and that's also a Q word because that is a pointer. Okay, so again, guys, I know I kind of went through really quickly here, so make sure to check this blog post, The Case of Curious Imp, and also the intricacies of Microsoft Compilers Part 2 that my friend wrote. What you can do, you can just search by imp with like underscores, and it will give you 2 blog posts right here that you can read. Okay, guys, at this point we have our little rundown routine written in assembly, and to be able to use it, we actually have to declare it in our file. If you skip all the way up to the top, let's declare it here as an extern so that the C file or C++ can locate it. So what I'm going to do, I'm going to take this, kind of like the prototype, and just put it here. No, it's not an extern. Now in this case it's void. It's a standard call and KAPC. and that should probably do it. Now before I just declare them like this, let me just write a little comment here and just say that the following functions are imported, let's just say defined in the assembly file. And at the end we can say end of functions defined in the assembly file. It just kind of like tells the next developer where these came from, kind of like for readability. Okay, so we defined one, and if you remember, we have 3 more. But before we go any further, oh, by the way, yeah, here's the problem. It's not a procedure, it's a rundown routine. Okay, so that's important. And just to make this thing work, not work, but just to test it, so I'm going to null these out, and I'm going to try to compile it to make sure that it works. So let's do driver rebuild. Okay, so we have a problem here. Oh, unreferenced local variable. Let's just do unreferenced parameter. We'll deal with it later because, again, we don't have anything here. We'll obviously add some code. So let's just build it. And initialize status used. Now let's see what is going on here. Oh, and here's a little bit of a problem. I'm glad that compiler found it. So we have the status variable, and it is not declared anywhere else. So yeah, right here it will definitely use an initialized value. So let's fix that. In this case, it's really simple. We just need to like set it here, and let's just say status. Well, let's just find some error. Bad, not bad, but bad data. Okay, so in this case, let's see if we can compile it. And by the way, those errors, I mean, not the errors, those warnings are very, very useful. Okay, and we have an issue here. For some reason, driver object is unreferenced. I'm sorry, we don't have a reference to it now. How so? Let's just go back. It's G driver object. Oh, obviously there is a misspelling here. It's drive, and that's the problem when you type so fast. It has to be driver. Obviously driver. Okay, that should probably fix it. Just a typo in the name. And here you go. So we can build it. So let's go back, and we were in our InjectDLL. Okay, so let's add kernel routine, and pretty much just do it here. It's a procedure and end procedure. Again, unfortunately, assembly is not very well highlighted, so I'm just adding spaces here so that you can see it better. And well, as always, as I did before, let's bring in the actual declaration for the kernel routine, and this one is somewhat large. And the reason I'm doing it here is so that in assembly language we can actually see, you know, what's being called, because again, you don't have the luxury of the C highlighting and stuff. And here it will just give us this long way of writing this routine. But anyway, we can refer to each of these functions, and just for the simplicity, I'm just going to put void in here. Now that's interesting that there is a p void, in other words, that the void pointer to pointer, so make sure to, you know, kind of like keep that noticed. And over here we just have a single void. Let me just put p void like so that we can actually see it better. Okay, so this is the way the kernel routine is declared. And let's put a little bit of a node for ourselves. Let's say pointer2, because again we will have to use registers here. So if you remember the calling convention for x64, it's RCX, RDX, R8, R9, and then we have another parameter here. So RDX, then we have R8, R9, and then because the next one is not passed in a registry, it is actually passed in on the stack, and that goes right after the shadow stack, which is 28H. And let me just align these things so you can actually see it better. The reason I'm spending so much time on comments, by the way, is so that the next developer or even myself can understand it better. Because if you do it like so, it will be pretty easy to work with this code next time, instead of just trying to spend time to actually see what the heck I was doing here. Okay, so again, we need to call our kernel routine, but before we do that, we need to adjust the stack a little bit. Let me, for some reason I want to put C comments in here. Okay, well, before we do that, let's actually write our kernel routine. Let's just skip all the way down, and we kind of will do similar thing for the kernel routine. And let's take its name from over here. Basically say kernel routine procedure. And again, we add this little suffix procedure so that we can differentiate. And yeah, so pretty much it has the same return value, except it has way more input parameters. Let's just take it from here. I'm going to simplify this thing because it's just too much typing here. And I'm going to put this here. I'm going to put this here. Yeah, I'm just gonna kind of prefer to have them on one line. Okay, so that basically gives us, let's just move this over here. Gives us this little definition of the function, and let's just say, you know what, we can just take it from here. Again, a little comment that it's called from RundownRoutine callback, and we also need to add a little comment here that it runs at that APC, that URL. Let's just say info. And let's say, you know what, no, let's just type our own message here, and let's say that it runs first at APC URL before normal routine, and you may adjust parameters passed here for the normal routine. So basically what you see here, like these parameters, the reason they're passed as pointers is that you can adjust them before they're called for the normal routine callback, but we're not going to be doing that. And return value is the same. If we want to return true, it will do the dereferencing. And in here, let's just check that we have our APC here, the pointer to the memory that we allocated. And let's say we'll create a variable here, deref driver object, and initially we say yes, please dereference it, and we return it here. And this is kind of like our way of telling our callback stub if we want to do it or not. Okay, so at this point we can actually use this routine here. We can actually call it from our driver. Let me see. I mean, from our assembly stub. Now, before we call it, we actually have to adjust these parameters on the stack. Now, as you see now, these parameters we don't have to change, but this one actually needs to be pushed down because, you know, right now it's allocated for this call, but because we will add stack here, it actually has to be moved. Before we do anything, we actually need to we need to move this parameter. Let's just say move, and let's just call it here for the forwarded call to kernel procedure. And the way we do this is just use, let's say, move using RAX, and let's see, RSP plus 28H. So again, this parameter, and we move it into RSP plus 18H. Now this offset, again, if you write them down the way stack is laid out for this call, you will see why it will be at 28H at this point. And then the next thing we need to do is align stack pointer on the 16-byte boundary for the kernel function call, and restore it afterwards. So the easiest way to do it is just by doing push. Let's just push RAX. It's just like, you know, we can push anything pretty much. And let's just kind of like right here, basically when we do push RAX, it gives us 8 bytes. And then we can do call. It also gives us other 8 bytes. So, right? And that's how we get 16. So again, push RAX, it's 1. And call is another one. So that's how we align it on 16-byte boundary. That's why we do this push here. And then basically when we are done, remember, like, the result from this API will be returned in RAX. So we need to test RAX for 0 and return our stack back. And let's see, what else do we need to do? Oh, before we actually call, we need to save our return address. Well, let's just save it in the shadow stack. And the shadow stack is this these 20.h or 5 keywords that we have to leave in the stack for every non-leaf function. It's according to calling convention. So right now we'll just save our return address in there because, well, why not? Let's say we need RAX from RSP, and then move RSP plus, well, I don't know, let's do 20 since it's the last cell. And that's how we save it. Again, the reason we need to do it is so that we can return from this call, because this call here will potentially override it. Well, after we come back from it, though, we need to restore our return address. And the way we do it, we read it again from the same location, and then we write it back into RSP. So very simple. Next one, we act depending on return value from function from kernel routine procedure, again from this one, which will return Boolean. And if it returns Boolean, if it returns 0, we just don't do anything pretty much. Just return, kind of like what we did here. And if it did not, we just need to invoke this function, which is again kind of like our way of doing that safety call. And you know what, let's just put a comment here. Let's just put important, because you know some developer might look at it and say like, what the heck, like why can't we use just a call here? So let's put it here. So we need to invoke this function via a jump, because it will be freeing the driver. And let's just see driver memory that our code runs from. Thus, not this, but thus, we can't return into it via a call instruction. Make sure to put an exclamation mark. And also, let's copy the same thing over here so that you know it also explains it as well. Okay, so that will be our little assembly code here. And let's go back. So, and that's our little stub here. So the last thing we need to do, we actually need to add it into our extern declaration here. So we don't need this, and the original API is actually void. So we provide that and provide this. And let's see if we can actually call. Oh, I keep making the same mistake. That's the problem of copy and paste. It's just a kernel routine. And let's see here. Let's see if we can call it. And over here, we need to provide an extern for our kernel routine. And let's see if we can compile it. Okay, so we have a couple issues here. Basically unreferenced parameters. So let's just quickly do that. So APC, normal routine, normal context, system argument, and system argument 2. So let's see if we can build it now. Okay, it built. So the only thing left is to write a normal routine, pretty much like we did before. Okay, guys, and pretty much the last procedure that we need to implement in assembly is this normal routine. Also, you know, I just realized I kind of quickly went through this stuff about moving registry values around, stack values around, so I probably need to explain this a little bit, so let me do it right now. Okay guys, so to explain these things that I'm doing, I wrote a little thing on my notepad. Now unfortunately my Wacom tablet is acting up, so I can't use it, so let me show it like this. Okay, so if we take a look, now this part of the diagram, this here, that's the location of the stack as we get, right when we get into kernel procedure at this point. Here's the layout of the RSP. So at the address +0, we get the return address from a function, which is keyword. Then we have 4 keywords as a shadow stack. And by the way, these values are all in hexadecimal. Okay, so 4 values of a shadow stack, and as you know, the shadow stack, if you look here, the values on it are passed in registers, so there's really nothing in there. So a shadow stack is basically available for this function to use for its own purpose. And then the fifth parameter, because it didn't fit into the shadow stack, it's passed on the stack, and that is +28, which is pointer to system argument 2. So this is how RSP would look like at the entry point into kernel procedure. Now, if we look further, the RSP would be changed here when we push RAX, and then when we call. So if I bring my diagram back, let's see, here you go. Fortunately, it doesn't fit into one screen. Let me scoot it over like this. Okay, so if we look, this is how the stack would be inside the call to a kernel routine procedure, or this one. In other words, we do one push, which RSP will go here, and then the call will push it back by one keyword. It would put return address from kernel procedure over here. Now, because we are passing these 4 parameters in registers, so we don't really need to change the stack. The only thing we need to do, we need to move this, which is system argument, from over here to over here. And that is what we are doing right here. So let me bring my diagram back. You see, so we go from 28 plus 28H to plus 18H. So we move this argument from here to here. And then the next the move here is when we are saving return address in the shadow stack. So what this means is that we have our return address over here, and if you look, this return address will actually be in the shadow stack for our kernel routine procedure, which is not good because that procedure can override whatever is on the kernel stack. So what we need to do, we simply need to save it somewhere outside, and somewhere outside the first parameter would be this +20H. And that's what we're doing here. So we take return address from here and we put it over here. So this is kind of like the second step over here. And that's just basically the only purpose is just to preserve our return address, because obviously we will need to return from kernel procedure, or from kernel routine. And then when we come back, we pop the stack and read the pretty much value back. And let's see, if we look at here, we just pop these 2 values and then we get to the same layout, and the only thing we need is just to revert this address back to what it used to be. We take it from here and put it back over here. So again, if we look in our code, that's exactly what we do here in the highlighted part. And then when we're done, if there is nothing else that the kernel procedure wants us to do, in other words, if it's returns 0, and the reason and the way how we check it is by doing the test operation here before we override RAX, and test sets the flag, and if it's 0, we basically return, and if it's not 0, we set up our call for object for dereferencing the driver object. So that's what we did. Again, I'm sorry I didn't explain it originally, so that's kind of like all what of these things are doing. Okay, well guys, I know that this video is getting kind of long, but let me do the normal routine real quick. That's the only one that is left here. So let's give it a little space here. This is procedure and end procedure. And again, let me get its definition. Here you go, normal routine. And again, the only reason I'm putting it here is so that we can actually see what's going on with our stack and the other registers here, because again, assembly is not as readable as our C. Okay, so in normal procedure, what we have here is that RCX, RDX, and R8. So this one is really simple. RCX is a normal context, RDX is system argument 1, and R8 is system argument 2. Okay, now at this point, let's go and code our procedure. I'm going to get it from here. I'm just going to place it here. And I'm going to call it normal routine procedure. Again, this is the procedure that is called. Well, let's just put a little note here. Let's see, it is called after kernel routine at passive call. Now this is important because this means that we can do way more stuff here, and we have the same condition here. Let's make sure that our APC pointer is valid. And this one, actually, let's return true to dereference our object by default. And let's take a look. So normal routine, it's a little bit different. Let's take it from our assembly here. Okay, so we have normal context, we have system argument and system argument 2. And let's see what else. So yeah, we'll fill it in later. What we need is just provide couple and reference macros, because again, the compiler will be complaining. So let's do it here, here, and here. And again, we'll fill in the logic later. So, okay, now at this point, we can call our normal routine. But before we do, we need to actually declare it as external procedure. Oops, procedure. Okay, well then pretty much let's do the same thing. So first call our procedure from C file. Now the good thing here is that we don't have anything passed to us on the stack, so all we have to do is just to use registers, which is really nice. Now in this case, the only thing we need to do is just to provide a shadow stack for the function, and then reclaim it back. Now this looks like totally unnecessary thing, but again, this is just a calling convention, and what we're doing here, if we look at our situation here, our diagram, you see like these four, that's what we're doing here. We're basically just reserving this space here on the stack before we call the function, and that's the only reason. Again, by calling convention, any non-leaf function, which means the one that receives some arguments, has to have this thing. Again, just a calling convention, there is nothing else to it. Okay, and then we pretty much can just do copy and paste of this code, because it's just one-to-one. Let me just do it here. And the only thing we need to do is to test RAX against itself. And yeah, so if we get 0, we just return. If not, we call our object dereferent object right here. So that is pretty much it. Let's see, we don't need anything else here. And then if we go back, we need to declare an external declaration here for our function. And it is also void. If you look at the normal routine, also void, doesn't return anything. This is a normal routine. And we put semicolon here. Okay, now obviously this is not here. Okay, and now all we have left to do is actually call it. Well, just need to uncomment this so that our procedure is included in the APC initialization. So let's try to build it. Let's see if we made any boo-boos here. And oh my god, it's building. There's no boo-boos. And that's pretty much how you code it. I know, guys, this kind of a thing is really long, so make sure to review this assembly function, assembly file. And you know, at this point I will stop this, and I will finish the rest in the next module. At this, I'm saying thank you very much for watching, and see you next time.